All right, I see people have stopped joining. So let's start with the digital session. So first of all, I'd like to welcome each and every one of you on the webinar. Does the lack of data prevent you from working with AI? The digital session has been provided by Radix and Microsoft. I think Microsoft doesn't really need an introduction, so I'm going to introduce Radix very quickly. All right. So who is Radix? We are an artificial intelligence agency. We basically invent, design, and develop robust and innovative AI-powered software solutions. And I think our main services are threefold. So the first service that we have is discovering AI opportunities with our clients. So basically through workshops, through talks, through looking at some data. The second service that we deliver is delivering the AI solutions themselves, so the implementations, so both for proof of concepts, MVPs, and productionizing actually models, for example. And then the third service that we deliver is building AI teams. So together with the AI team of your company, for example, we look at how we can do things, we do transfer of knowledge and so on. So that's basically the three services that Radix provides. Now we're trusted by a few customers that you can see here. So some big names are GSK, Proximus, and House of HR, for example, but hopefully many more to come. All right, so now that you know what Radix is, maybe who we are, I think that's also quite important. So me, myself, I'm a machine learning tech lead at Radix, and Jeroen Bolle has also joined me from Microsoft. Maybe Jeroen, you can tell something about yourself or your function.
Sure. So my name is Jeroen Bolle. I'm a senior data and AI specialist at Microsoft. So I work with large commercial enterprises, both in Belgium and Luxembourg, on enabling a data culture and supporting that culture with data and AI capabilities on Azure.
All right, awesome. All right, so maybe some practical information. So if you have any questions during the talk, you can just put them in chat, and I'll try to notice them and give you an answer. There will also be polls and questions so that you can also answer in the chat window, and you will, of course, receive a recording of today's digital session. All right. So what I would like to do, I would like to set the scene first on why we are organizing this digital session about this topic. Afterwards, we're going to discuss some methods to deal with little data. Then we're going to look at some services to deal with little data, and then we're going to review some use cases, both from Azure and from Radix itself. And then you can, of course, ask some questions. All right. So let's start setting the scene. So what I'd like to do first is to say that I think AI is great. AI is great. I think it's everywhere around us. And you can see some examples here that you probably will recognize. So face detection, for example, works really well. You have translations, you have email filters with spam and so on. And it actually makes our life a lot easier. And if you think about what the applications of AI could be, there are so many. So the first thing I want to say is AI is great. Right. The second thing I would like to say is that AI can create value. I think that's also something that's people already know and already believe in. And I think this is an example of a study of McKinsey, for example, that just looks at what the impact could be of AI for every sector. Now that you're joining me in this nice weather on a Friday, I think also makes proves that you guys think that AI has a lot of value. Now, it's great, it can create value, but it also has its challenges. Right? I just have two examples here, which you might know. So the first one is in computer vision. So there are a lot of algorithms that are trained to just detect a certain image class, for example, a panda, a gibbon, a dog, a cat, and so on. Now, there are adversarial examples, and what basically happens is that if you have a model and you add the right noise. So this is something that, of course, you have to look a bit for. But if you add the right noise, you can mislead the computer vision algorithm. And so this is called adversarial examples. It's something to watch out for, but like this is one of the challenges. And then the second challenge is that there are some misconceptions about AI, where you can, a lot of people think AI is some magic, for example. But I would advise you, if you have some time in the weekend, to look at the RoboCup World Cup, which you can see on the right, where you can see that AI is not yet there. All right. So maybe a first question: who has ever discarded a project because of data size? And you can answer in the polls window. So I see Daniel already Did it, Samuel, also? Yes, so it's now live. All right, I see a lot of yeses, so 7 yes and 1 no. And that's exactly the reason why I want to do this digital session today. And I actually like to start with the takeaway message of today, the take-home message. And for me, that's a perceived lack of data does not mean that the project is impossible. Now, of course, you don't have to take my word on this. What I would like to do in what comes is to make you feel the same way, that you, after all that you have heard of me and of Jeroen, that you see like, okay, maybe I should rethink my project. So that's the goal of today, not on how you should do it exactly, but just that you know that a perceived lack of data does not mean that the project is impossible. Now, before we go to the tools and the methods that we can use, I would like to first define a bit what is little data. And so let's start with what normal data is, I think. So normal data set mainly contains two components, I would say, like very high level. So the first one is the amount of data points, and that can be structured data, it can be just rows in a table, it can be images, it can be text, it can be time series. But the first thing is the amount of data points, and the second thing is the amount of labels. And you see some examples here. So these are like some quite known data sets. So we have the wine quality, for example, together with some features. So this is what we call features. It's what defines a data point. And then you have images, for example, cats or dogs. Or you can have text, which is, for example, which have descriptions of a certain movie, and then you can predict the genre, for example. So that's like three very famous data sets. But this shows what a data set can be. So it's about amount of data points and amount of labels. And so what normally happens in the normal case when you have enough data is you do supervised learning, and that's the most common machine learning approach. So what supervised learning does is actually you have a certain model. You can see it a bit as a black box. And what you do is you just feed it training data, and by showing examples of, for example, images of apples and cupcakes, at the end, it will come up with some rules to define apples and cupcakes. And so by just going over these examples over and over and over again, it tweaks what it thinks a bit every time. And at the end, it can form quite a good model. Now, what's important here is to note that if you want to do this, of course, the supervised approach, then you need lots of images of apples and cupcakes, and you need a label for each of these images. And so this is where the hard part sometimes comes in, where the challenge comes in. All right, so now I would like to focus on the different types of little data, and why I say little data and not small data, for example, of a small data set, is because it has these different types. And it can be that even when you have a huge data set with no labels, for example, you could still call it little data because it's only little useful data, for example. So that's why I'm talking about little data. So what we saw first is when you have a lot of data points and a lot of labels, so you can put your X here, and that's the normal, I would say, supervised case. Then a second one is when you have a lot of data points but only a few labels, which can be more challenging, and this can look like a very big data set, but in reality, it's not always the case. And then you can have, of course, a lot of data points but no labels. You can have few data points and few labels. And then you can have no data points and no labels. So your data set can be somewhere in this entire lower triangle. And where this exactly also defines a bit on what approach you should use. So it's very important to know that there are several types of little data. And so it's really always some kind of creative process to see what works best in your case with little data. All right. So why work with little data? That's the second question I would like to answer before going to the methods itself. So why work with little data? I think this graph says it all for me. I think the potential value of AI use cases is well established. But what's really important is that most real-life data sets are actually limited in size. And that's what you can see on this graph. You can see that the most of the very big data sets are from research or from big companies. But actually, in real life, this is where you want to focus on. We as consultants and in industry, you'll very often see that there is a large number of providers with very small amounts of data. And that's why I want to focus on this, because this is, I would say, the value adding for in real life. And that's why we want to deal with little data sets. All right, so maybe let's start with methods to deal with little data. All right, so I'm going to give a few examples of what you can do with little data, and I'll try to divide it in the types. So we saw before we have few data points, few labels. I think this is the most standard case after just the supervised learning. So it's just all the data points can be labeled, but you don't have many of them. All right, and so the first technique that we can use here, I'm going to start with computer vision, but this works in other fields as well, is data augmentation. Now, data augmentation, as the name says itself, it creates or enlarges your data set in an artificial way. And what is an artificial way? It just adds small transformations. And you can see here this cat, it looks every time the same for us, but this is not the case for a computer. A computer sees this image differently. If you just look pixel-wise, for example, there will be a lot of difference between the pictures. And so basically, what a computer vision model sees in an image is not just a cat or a dog, for example, but it just sees a block of numbers, which is like the height times the weight times 3 for the RGB channels. And that's basically what the computer vision models see. And what in computer vision often happens is you just do convolutions over a processed image. So this is what you can see in the image right here. So you can see we just extract some features for this window, then we push the window to the right, then we extract features again. And so it looks at the image as squares, actually. And so if you just add a little rotation or translation or a bit of scaling or adding a bit of noise, it's a completely different picture, or maybe not completely different, but it's a different picture for a computer. And in that way, we can just augment the data like 10-fold or 20-fold by just doing these kind of things. All right, so if that's clear, we can actually do the same for NLP, and there are several methods. I think this is a fun one, also based on AI, for example. So in AI, we have a lot of models that can do translation, for example. So one of the ways to do data augmentation in NLP is to take a certain text, translate it to another language, and translate it back. And then you have actually, if you have a good model for translation, then what you get, the augmented model of the augmented text is not exactly the same, but it has the same context. I have no time, I do not have time, and that also adds to your data set. So actually, data augmentation is also popular in NLP. You can, of course, also have other things where you can do word replacements, leave a word out, add a word, for example. So by adding a bit of this noise, you can just create different training examples. All right. For the next technique, I would actually like to ask a question. And it's a very basic question. It's like, how would you describe a house? If you just look at it, how would you describe a house? So please put your answers in chat. All right, I see a lot of similar answers. All right, great. So how would you describe a house is actually a very basic question, of course, but it's not something that you can easily answer as a computer. So the next technique that we're looking at is transfer learning. What is transfer learning? It actually builds knowledge on one application where you assume that there's a lot of data, and then you try to extract knowledge from there and use it to train your model on a small amount of data. And this happens a lot in computer vision, but also in NLP, for example. But why I asked this question is because if you do this, instead of learning from zero, you start training by using your knowledge. And that's also how almost everyone answers the question, what is a house? If you answer the question, what is a house? You say it's a big box with windows and a door, for example. So what you do is you just take like smaller level concepts, like a big box, windows, and a door, and that's how you try to explain what a house is. And it's actually the same with transfer learning. You just look at things that you already know from another example, from another application, and you try to use them in your application. So, for example, if you want to know how a dog, a cat, or a horse looks like, you can use the same features, right? This is what we call features. It can be, for example, we're looking at the paws, the teeth, tail, and so on. So that's basically transfer learning. You just take knowledge from another application, and so in our case, where you have a lot of data, and then you just fine-tune it on your own data. And so why this is possible with machine learning is actually because of this. So this is from NVIDIA, and it actually shows you how a neural network sees. So a neural network is a machine learning model that is very often used. So I think the words deep learning will probably ring a bell. But so what it does is it's every layer of your neurons, it learns different features. And so what you have is in the first layers, you actually just see, like edges, corners, rounds, for example, in different orientations. So this is like very low level features. And then in the higher layers, what you can see is, for example, wheels, doors of the car, and so on. So by just looking at next layer or higher layers, you also see higher level features. And that's exactly how transfer learning works, because you can train something on data, you can add or you can extract these kind of low-level features, and then you can fine-tune it on your own application. So that's transfer learning. All right. So here you can see another maybe more clear example. So this is your neural network. Every layer has other features, more high-level features. And what you do is you train this on task A with a lot of data. You freeze these, what it has learned in this. So this is like the knowledge, you transfer it to your own application, and you only train the last layers. And that means that, of course, you need a lot less data because you only need to train part of the model. All right, and what's really great about transfer learning and, for example, computer vision, and also NLP, by the way, is that there are a lot of open data sets that can help us. So, for example, for image classification, you have the ImageNet dataset, which has 1,000 object classes and like 1.2 million training images. So these low-level features, you can train them on there. And very often what is done there is that you just have your own application. You take a model that has been trained on this open dataset. Everyone can access it. And then you fine-tune on your own data. And that works actually really well. And instead of having needing to have, like, for example, thousands of images, it goes to tens or hundreds of images. So that's transfer learning. You have the same for object detection. Object detection is where you want to just have a bounding box around a certain object that you want to recognize on an image. And for example, there you can use the COCO dataset. It's something for object detection. It also have a lot of classes, and it's just keep on growing. All right. Then if you look at transfer learning in NLP, it's actually basically the same idea. So we want to extract knowledge from a big source of data. So if you think about the big source of data for NLP, for natural language processing, then you can go look at the Wikipedia corpus. It's very big. You can just extract it from the internet. And basically what they do, and that's called a language model, is they try to predict which word is missing from a certain context. And by doing that, you can create a mathematical representation of your text. And that actually works quite well. And then you can fine-tune this on further downstream tasks, for example, classification, summarization, question and answering. So you can just basically use the entire knowledge built up by looking at the Wikipedia course and then fine-tune it on your own model or your own application. So that's the same thing as with computer vision, but then in NLP. So one of these models is called BERT. It's maybe a bit more technical detail, but this is like the state of the art, and it actually leads to a lot of improvements the latest years in transfer learning in NLP. All right, so we had data augmentation and transfer learning, which applies to few data points and few labels. Now let's assume that we have many data points and no labels. Then, of course, we can also do things, and this is called unsupervised machine learning. And so basically what it does, and it's about the same for all the different techniques that you have, but you just try to find structure in data without knowing any label. And you would think like, okay, this is a bit harder to do if you don't know what structure you're looking for. There can be several structures you look at, several groups of data, and so on. So here, the interesting thing is to really know what you're feeding to the algorithm. And so, for example, what you have is distance functions, clustering approaches, anomaly detection. But the most important thing here is that you know what you're doing and that you just feed the data that is relevant for your application, for example. And if you just feed the data that is relevant for your application, then you can find really nice groups for this kind of thing. So here, of course, there are also a lot of use cases known. I'm just thinking at fraud detection, for example, is anomaly detection. So this is also really interesting, but you have to know what you're doing here. And making the assumptions that you do. All right, then let's have a look at lots of data points and few labels. There you have semi-supervised learning. Semi-supervised learning is actually the combination, of course, of supervised and unsupervised learning. And so what you're trying to do, and I will give you an example a bit later, is simultaneously trying to make use of the labeled data that we have. So this is supervised, and then the structure of the unlabeled data. And so one example is active learning, where you just do clustering first or do classification first, and then label the ones that you're unclear about or are seen as noise. And then you can build up like this. So it's mostly iterative. Now, one of these semi-supervised algorithms is unsupervised data augmentation. And there's a very good reason why I want to show this one on the next slide. But maybe let's explain it first. So what unsupervised data augmentation does is it has two parts. You can see here the left part is a supervised. So this works quite the same as we have been discussing. So you show a certain example, you know the label of it, you just tweak your model a bit, and then every time it goes over and over again until it reaches a certain minimum in its loss function. Now, actually, we have a second part, and this is the unsupervised part, where you actually have unlabeled data. And so what we have with the unlabeled data, what we do with it is, instead of just looking for groups, for example, what we do is we add augmentations. So it's actually a combination of several different methods. So you add certain augmentations, but you assume that when you add augmentations, the image, for example, or the data point, it should have the same label because you only augmented it very slightly. And that's something that you can use with an unsupervised consistency loss. So you just take the unlabeled data, you add an augmentation, and you say, okay, at the end, what the model predicts should be the same for both the basic image, the unlabeled one, and the augmentation. And also by doing this over and over again, you learn some consistency in your data, and this seems to really, really help a lot when you're training your model. All right, and so the reason why I want to show you this one is because I really like how they state the results and what how they report on their findings. And so what you can see here is the error that you have when you're with your training and test set. And so the lower is better, of course. So if you have an error of 0%, then it's fine. If you have 100%, everything is wrong. And what you can see here is first, I think most important one, is if you look at the pre-birth state of the art, so to say, you can see with a lot of examples, like 25,000 or 650,000, or like with these many examples, you have an error that is quite okay. This is the state of the art for the application. Now, if you look at the second part, the semi-supervised setting, where you use the unsupervised data augmentation, you can see that for the same data sets, I wouldn't say that they work better, but they almost have the same accuracy with like 1,000 times as few data, which is really crazy. If you go from 25,000 examples to 20 examples, for example, 20 examples, then it's really good that you can do it with that small data. And that's things that we have seen like over the past decade, and these kind of algorithms really help a lot. So I'm not saying that every application, of course, you can do with 20 data points, but that there's a decrease in the amount of data needed is really awesome. All right, and then you have some different methods that don't really fit into a category. I just would like to mention two. The first one is you have some standard things, but you also have creative approaches. I'd like to just give one example. So imagine that you have a computer vision application, and you have 100 classes, but for each of the 100 classes, you only have 5 images. And that's, 5 images is not a lot, even with data augmentation, and can be very challenging. But you can do something else. And then what I try to do, for example, is can we change the objective? And if you have a look, what you can do instead of just saying, okay, this image is this class, which you only have 5 examples for, which is really hard to do. What you could do, for example, is a pair of images from the same class. And then you can train your features in this kind of way. And the only thing that you want to predict is not which class it is, but if it's the same class. And then you just have pairs of data instead of one data point. And this can really increase the amount of data that you have to train features. And then after training good features, you can just add a last layer on your model. And so what you actually do is you go from 5 images per class to the combination or just pairs from these 500 images to learn relevant features. And I think if you look at the combinations of 2 out of 500, it's a really big number. All right, and then the last one, which I would also like to mention, is the simulated data. So actually where you can make use of simulation environments to gather data for a specific problem. And this is very often done with game engines, like with Unity, with Driver. I think everyone knows the examples of Grand Theft Auto, for example. So where you train, it's also transfer learning. So you train a model on the simulated data, and then you fine tune it on the real life data. So that's also a cool one to use in your projects. All right. Then after these methods, I think it would be cool to go to Jeroen and to see also which services you can use to deal with little data.
All right, I'll make it fast because we don't have that much time left anymore. So basically, I guess you all know Azure, right? It's a Microsoft public cloud platform. We have a set of proven, secure, and responsible AI capabilities on Azure. And you can basically categorize them in these three domains. On the right, you see the machine learning, which is for building your kind of advanced custom machine learning models, as well as do the inferencing using any kind of open source or any open framework you want to use, as well as manage any processes related to it in terms of monitoring MLOps, managing data drift, and so on. The second pillar we have is knowledge mining, and this is basically a set of services we offer for intelligent search indexing. So you can create a search index and then apply AI algorithms on the fly on it to extract text from documents, do OCR, key entity detection, and so on. And the third one is what we call AI-powered apps, which is basically the main topic today, is really, these pre-trained AI services we offer that you can embed in applications or in big data processes and so on, which will allow you to work with AI models without any training or with very little training or data input. So where is this coming from? So basically, we have a very large research division at Microsoft. I'm not sure you're aware. It's thousands and thousands of researchers across all of the world, based in China, the US, in Cambridge, in the UK, so in India. And these guys do a lot of research on next-gen technology with a big focus on artificial intelligence. And we also embed a lot of these results they do, the results of the research in practice in other products and services from Microsoft, for example, Microsoft Teams, Microsoft 365, and in Xbox, for example, meeting transcriptions, speaker detection, designer capabilities in PowerPoint, and many others. And just want to quickly share that you can access this research online. So we have a research portal with different research areas which you can just access. And there's a lot of research papers on different topics on artificial intelligence published there. What I want to mention in particular is one we published very recently on NLP, because it was mentioned by Brecht, and we actually have the state-of-the-art model now. It's an open source model called DBERTA. It's kind of a next-gen BERT model, which has, the best score on the Superglue benchmark for NLP right now. So if you're interested in NLP, have a look at that, definitely. Going back to the presentation, so basically, if you look at these pre-trained services, AI services you can embed in applications, we offer many different ones. And basically, you can categorize them in four main domains: vision, speech, language, and decision. On the vision side, there's there were some of the first AI pre-trained models that were released. So in the area of computer vision, for example, for object detection, but also for image classification and detection of text and images, as well as content moderation and images. These are all scenarios that are supported out of the box. We have many others, for example, for face detection, as well as facial recognition, facial verification for identification purposes, as well as services to extract content out of tables from pictures of documents, as well as key value pairs through form recognizer, and many others. On the speech side, we have many different text-to-speech, speech-to-text, ready-to-use services, as well as speech translation services for both batch and real-time use. as well as the ability to do speaker recognition through speaker identification, as well as speaker verification for security reasons. On the language side, we have many different ones, very well known for bots, for example, is language understanding, which allows you to do for both voice and text, speech and text, to detect the actual intent in a certain utterance, but other services as well for example, sentiment analysis, key phrase extraction, entity detection, and so on and so on and so on. And then on the decision side, these are lesser known services because they're more applied. We also have pre-trained services, for example, for anomaly detection, where it can ingest any kind of real-time or batch streaming data, time series data, and choose the right algorithm to detect anomalies based on that. As well as we've built a metrics advisor on top of that you can get recommendations on, which kind of attributes are influencing the anomaly. We have others like Personalizer, which I will actually demonstrate in a second. It's important to understand all of these are cloud services, but some of these models can be deployed to the edge or in any kind of container-based deployment. So many of them, for example, for IoT scenarios or other scenarios, you can deploy outside of the cloud. And some of these can also be customized to your specific needs or business context, so they allow to upload or to train or to customize based on your specific needs and data you might have. So why cognitive services? Very quickly, basically 3 reasons: easy, flexible, and tested. Very easy. It's a REST API. It's very easy to embed in an existing application. You don't need any specific machine learning expertise, or at least very little. It's quite flexible, can deploy it both in the cloud or on premises or in an edge device. You can integrate it in big data workloads, or we have many customers also using it in business intelligence tools, for example, like Power BI or others. It has many different SDKs ranging from Python, Node, Go, Java, and so on. So you can use any kind of programming language to do the integration. And it has a quality kind of community and documentation. These are also tested models, so you can be guaranteed that there will be good results. So I want to end with 2 examples. One is Azure Personalizer, which is a lesser known cognitive service, which allows you to deliver a personalized relevant experience for every user. And it basically uses a reinforcement learning algorithm or approach. And it basically takes a set of input actions and chooses the best output based on a trained model. But it also does, and that's the reinforcement part, it also does exploration by trying out new combinations and really measuring the reward or the cumulative rewards based on the reaction of the user. And to bring that a little bit to life, I'll show a very quick demonstration. So basically, I have a website here. It's like a community website. And here the idea is to give kind of personalized content to my users. And I can use this personalizer cognitive service here and give a set of input actions. And here it's quite simple. I have a refer, social, direct, email, search. This is a tennis site, so I know also which tennis tournaments are ongoing. And then I have my user agent as well, or information based on that. And basically, it's going to select, based on this input action, out of a number of possible contents or content that is already pre-made. And it's going to then, basically, when I do it now, show a personalized article, it's going to make a selection based on my input. And now it's going to actually measure how I'm interacting with the content. So if I click on it and I read it, my reward score is going up. And basically at the end of it, after a number of time, it's basically going to, for example, if I send back, it's going to send back the rewards to the service and say, this user was very engaged. We see here, and this is basically why it's a reinforcement learning algorithm. It was basically using, in this case, I actually don't see it anymore, but if I click, It was using the learned model, but it can go in an exploring phase as well, where it just kind of tries to test out new possibilities and measure the user impact. So it's an example of one of these cognitive services. Another one, a new one that's currently in preview, is what we call spatial analysis. It's part of computer vision, and it allows, based on static camera placement, it allows you to define a polygon to actually record movements in physical spaces. And this allows for different pre-made kind of scenarios you can do. For example, people counting, but also doing monitoring over historical data of how many people were in a certain space, and do alerting on top of that. A very relevant one as well is it can do face mask detection, as well as social distancing monitoring. So you can set a kind of minimum distance and then measure and send alerts if the distance is being crossed, or just do the monitoring. But it could also do, for example, entry and exit monitoring. For example, use case would be NMBS monitoring the train stations if not too many people are taking certain trains. It's also very relevant probably today. So how does it work? Basically, yeah, there's some configuration you do. You send a JSON template saying, okay, I want to measure person distance events. In a social distancing example, I can set my minimum and maximum distance threshold. And basically, each time you deploy this model as a container on an edge device, usually it's going to be kind of Tesla, NVIDIA Tesla enabled kind of edge device, so something with GPU power. It's going to automatically monitor or process all kind of camera images and then launch these events based on the results of the model. So hopefully this gave you an example of different kind of capabilities we have on Azure and how you don't need any data or any kind of, a lot of input to actually use these models. Back to you, Brecht.
All right, thank you, Jeroen. All right, so next to the methods that you have seen and the tools of the Azure Cognitive Services, I also would like to show some real-life examples. I'm trying to keep it brief. So let's look at the first one. The first one is for GCF Counting. So basically what the context of the project is they have cultures on petri dishes, and now people are actually looking at this to see if there are certain areas of interest. And so these are like colonies of bacteria that have been growing. And so what we'd like to do is to do some kind of object detection approach. And so basically normally what you would have is you would need at least a few hundreds or thousands of images to make this working. So we tried to use the standard techniques that we saw before. All right, so you can have a look here at some examples. So you can see some examples of these colonies. And so basically the data set that we used is around around 100 labeled images. And so what we did is we applied two of the previous techniques. So one is transfer learning from the COCO dataset. So remember that this learns the low-level features that we need. And then the second part is data augmentation. And so these are some examples of data augmentation. So you can see here, this is the original image. And then you can see here the one, for example, this one is a bit scaled. And you can see here that this is, for the computer, a different image than this one. And I will also say for a human, actually, in this case. And here, for example, you see instead of just scaling, it's a bit transformed, it's a bit packed together. But this creates a lot of new training images for the computer model. And so what happens is instead of 100 labeled images, you go to a few thousand labeled images, and that really helps the case. And so in the end, what we achieved is actually superhuman accuracy. And it's up to 6 times less time spent on CFU counting. So this is like a real world example where you have a certain application and where by just creating a smart way of using your data, you can achieve a much higher accuracy. And so this is like the first use case. Then the second use case is for an HR partner or client is a vacancy parser. So basically what the task to solve is here is we want to identify and label sentences in free text vacancies. And so a certain sentence can be a company description, for example, it can be a job description, it can be about the offer. So we made these several kinds of types of what a sentence can be. And so the task is to just classify or to just say, okay, this sentence is about the company description, this one is about the job title. And you can see some examples here. So machine learning engineer was the title, and then Radix is a team of, that would be company description, and so on. Now, how we approached this, so we didn't have any label data, we just got the vacancies itself, but not like a label per sentence. So how we approached it is basically by first using a multilingual sentence embedding. So what that is it's maybe very high level. What it does, it transforms text into a certain mathematical representation in a certain space, and things that are close together also have the same context or the same content, are very semantically similar. So what we did is first go from text to this kind of point in space. Then we perform clustering. So we actually create groups with similar meaning. So the points that are close together have this similar meaning. So you just make a group around it, and that gives you these clusters. And then at the end, what you do is you label these clusters, these groups of data points instead of the data point itself. So actually what you try to do here is you just try to take advantage of the structure of your data, make groups, and then afterwards label these groups. And so what you can see, the model performs actually quite well. So what we of course have to do is we have to label a golden test set to know how well we do. We can just assume it will be working. And so at the end, what you see is it has an accuracy of 90% without labeling like a single data point. We just labeled the groups that have been found. So that's actually quite awesome. And so what you can see here, for example, as a machine learning engineer is counted as job title. Then Radix is a description of the company, and so on. So this is also another example where in NLP, for example, you can make use of these open models, like these sentence embeddings that have been trained by like the big companies like Facebook and Google and so on, and Microsoft, and just use it for your application. All right, so that's our 2 use cases. So I'd like to summarize. So I think the take-home message, again, is a perceived lack of data does not mean that a project is impossible. So I hope that I could show you some methods to re-evaluate maybe some use cases, or to just have a certain sense that you do not only need, always need 1,000 examples of data points. So that's the first message that I would like to bring. And then the second one is, I think experts can help you, of course, to find the best methods to get value of your data. So if you want to have a talk about something, you can always contact, for example, Radix, or it's just an expert that can help you find the best ways to use your data. All right, thank you, everyone. And would there be any questions? Then you can put them in the chat.
I don't see any questions, so I think it was quite clear, I guess. And I have to run as well. So thank you very much. Or is there a question? Thank you very much for joining. And please don't hesitate to reach out if you have any further remarks. Have a nice weekend.
Yes, have a nice weekend. Enjoy the sun. Bye.